Hi, everybody. Welcome back to Dave's Math channel. I'm your host, David Tare, and this is my continuing feature on the Math Lovers book. And today, this is going to be my final lesson on rotation groups and symmetry groups of platonic solids. We've already looked at 5 out of 6 of them, namely the rotation groups of the of all 5 platonic solids, the tetrahedron. That's called the tetrahedral rotation group. Also, the cube and the octahedron, which have the same group structure, that's called the octahedral rotation group. And finally, I did the icosahedral rotation group, which is the rotation group of both an icosahedron and equivalently the dodecahedron. And today I'm going to talk about the last of these groups, namely the icosahedral symmetry group. It's also the biggest of these groups. It has order 120, and it turns out it's isomorphic to S5, the symmetric group by 5 symbols. Anyway, let's begin. And I thought I was going to make another, paper cutout of icosahedron. I made this one yesterday. I'll probably just still demonstrate with this one. It's very tricky to demonstrate the symmetry group. It turns out it's tricky enough just to do the rotation group. I think I managed to do that yesterday. But the trick is, if you want to get the full symmetry group, this involves reflections as well as rotations. You have to be very careful about how you reflect it, it turns out. And it turns out, at least for a dodecahedron, which I didn't make here, dodecahedron actually has a really interesting geometric structure to it. It turns out that there are, I think there's 15 planes that pass through dodecahedron that if you intersect them with the dodecahedron in the right way, you get a rectangle. Pretty amazing. You wouldn't expect this. I wouldn't think you would expect this. And the dimensions of this rectangle turns out to be a golden rectangle too. Pretty amazing. So the dodecahedron has 4 golden rectangle cross sections, and they all bisect the dodecahedron. They all go, if you look at the portion on either side, they're congruent. They're the same size, and not only the same size, but they're congruent. And I don't want to try to demonstrate that. I think it would be a little too complicated. You'll have to take my word for it. But what's interesting about this reflection, if you reflected about this plane, any one of these 15 planes whose cross section is one of these golden rectangles, it turns out you get all. If you number the vertices the way I was showing yesterday, also the way I did it in my book, you number the vertices 1 through 5, but you have sets of 4 of each number. So you have 4 1s, 4 2s, 4 3s, 4 4s, 4 5. It turns out if you did that, here I'm using letters. I guess in my book I use letters for the vertices, but I think you would get 4 different vertices if you did this, and if you reflected about these 4 vertices, and you see how the numbers got transformed. That transformation turns out to be isomorphic to an odd permutation of S5. So remember, we got all the even permutations by doing the rotations. Well, it turns out you get all the odd permutations if you also include one of these reflections. But you have to be very careful about how you include the reflections. You have to reflect precisely this way. And I do demonstrate it in my book. I don't know if I want to go through all the details, but it turns out if you first do the reflection, if that's all you do, I think you remember there were 15 of these planes. There should be 15 possible. If I did this right, it looks like I'm showing 20. Yeah. What do I say here? Oh, yeah, that's if you include one of the 24 five-fold rotations along with one of these reflections. You get another 24 elements. Because you got 20, remember you got 24 five-fold rotations, including the identity. Yeah, or no, not including identity. So if you reflect once, you'll get an additional 24. And it turns out I don't think it matters how you reflect as long as you do one of these reflections. And because we had 20 threefold rotations, if you combine those with a reflection, you get an additional 20. And then finally, if you do any of the 15 twofold rotations. Remember the rotations. I might as well, since I have this icosahedron here, I might as well demonstrate these three types of rotation. So fivefold rotation would just be a rotation about one of these vertices, and you can go counterclockwise, 72 degrees or 144 degrees, or you could go clockwise 72 degrees or 144 degrees. That gives you four, but then there's a total of what is it, six? Yeah, six pairs of opposite vertices, so you get 24 that way. And if you did the threefold rotations, I might as well go back to the slide where I talk about them. Yeah, remember, threefold rotation is something like this. You start with a face, and then you can rotate 120 degrees clockwise or counterclockwise. But there's 10 pairs of opposite faces, so that gives you 2 times 10 or 20. 20 threefold rotations, and if you combine with them with a single reflection, you get 20 of these transformations. Finally, the final type of rotation you can do is a 180-degree rotation, or flip about an edge, like that. And if you combine that with, let me try to show that right. It's a little tricky. So you do that, and then if you combine that with one of your flexions, you'll get an additional 15. And you also have the identity. Don't forget about that one. If you just did a single one of these reflections, you would get I guess the one I showed, you get an additional one. So that gives you an additional 60 transformations. They all correspond to reflections, and if you kept track of what happens to all the vertices the way I number them, or I'm supposed to number them, you would get all 120 permutations of S5. You get the even ones from just the pure rotations, and you get the odd ones if you also include a reflection. Pretty neat. So that's kind of a geometric what do you call it? A representation of S5, just a full symmetry group of a icosahedron. Who would have thought? And like I said, it's the biggest one. You'd have to go to higher dimensions if you wanted to get bigger, geometric representations of groups. And you could do that. People have actually done this. I might as well tell you, there is a four-dimensional analog of dodecahedron. And it turns out the symmetry group of that, I guess they call that a what? There's a name for a higher dimensional polyhedra. Complex, I think. Yeah, if you looked at the symmetry, the full symmetry group of the four-dimensional analog, the dodecahedron, that has order 14,400 or 120 squared. It's a really big group. I think it turns out to be a simple group, just like S5 or A5 is a simple group. I'm not going to talk about what simple groups are. I didn't even talk about them in my book. But there are certain types of groups, finite groups known as simple groups, and those are basically, you can think of them like elements. They're or prime numbers. They're groups that can't be simplified any further. It turns out that every group, whether it's finite or infinite, is either simple or it can be built up in a very complicated way from simple groups, just like composite numbers can be built up from prime numbers by multiplying them together. Or if you like chemistry, chemical compounds are built up from elements. So anyway, just thought I'd mention that. But anyway, that completes all of my discussions of the rotation groups and symmetry groups of Platonic solids. So thank you for watching. Long live math, and I'll see you guys next time. Bye.